In the previous chapter, we have discussed about some effects of current, like heating effect, lighting effect, and some more effect is there that we will discuss it in the third unit of physics, that is magnetic effect of current. What is magnetic effect of current? This is the phenomena by which magnetic field is produced around a conductor carrying current. This was firstly observed by a scientist H.C. Oersted. So this effect is also called Oersted effect. The magnetic effect of current is known as Oersted effect. What did he do in his observation? He took a conductor and passed it through a plane like this, through the plane, in such a way that this conductor is perpendicular to the plane. He connected the ends of the conductor with a source in such a way that current flows through the conductor in outward direction. And when he put a magnetic compass needle near it, he observed deflection in the needle. When he changed the direction of current flowing through the conductor, then he observed deflection in the needle in the opposite direction. Magnetic needle is a magnet, and deflection in it shows the presence of other magnet or magnetic field near it. And from this activity, he concluded that due to current, magnetic field is produced around the conductor, due to which magnetic compass needle gets deflected. He obtained two conclusions. Number one, when current is flowing in outward direction, then deflection in the needle takes place in anti-clockwise direction. And when current is flowing in inward direction, then deflection in the needle takes place in clockwise direction. Using this concept, Maxwell gave a rule for finding direction of magnetic field around a conductor. And according to this rule is known as right hand thumb rule or curl rule. And according to this rule, we hold a conductor carrying current in our right hand in such a way that the thumb points the direction of current flowing through the conductor. Then the direction along which the fingers curl will show the direction of magnetic field. If this is a conductor and we hold the conductor like this, conductor is carrying current in this direction, in the direction of the thumb, then the direction of the fingers will show the direction of magnetic field around it. This is called Maxwell right hand thumb rule. We have seen that a conductor carrying current can produce magnetic field. And at certain point or at a point, it will have some direction. and direction of magnetic field at a point is represented by drawing tangent at that point on the plane. As we know that tangent at a point on the plane is perpendicular to the plane, so we can say that direction of magnetic field at a point on the plane is also perpendicular to the plane. In the activity, in the experiment, Oersted experiment, we had taken conductor perpendicular to the plane. Here, direction of magnetic field is also perpendicular to the plane at a point either normally outward or inward. So we can say that at a point on the plane, magnetic field is either parallel to the current flowing to the conductor or anti-parallel to the current flowing to the conductor. There is a law which is called Biot-Savart's law. This law is used to determine the strength of magnetic field at a point due to a current element. What is current element? Current element means the elementary portion of the conductor carrying current. One thing you should know that this law, or we cannot find magnetic field at a point due to whole conductor directly. So firstly, we need to find magnetic field at a point due to elementary portion. And this is done using Biot-Savart law. Look at this figure. This is a conductor carrying current. This is the direction of current. This we have taken elementary portion of the conductor. And this is a point where we have to find direction of magnetic field due to this elementary portion of the conductor carrying current. So according to this law, the strength of magnetic field, that is dB, due to a small current element dl carrying a current I at a point P, distance r from the element, is directly proportional to I dl sine theta and inversely proportional to the square of the distance r. Here theta is angle between dl and r. This is the direction of dl at this point. And theta is angle between dl and r. So mathematically we can represent it as dB varies as L, dB varies as dl, dB varies as sine theta, and dB varies as 1 by r square. When we combine all these, we get dB varies as I dl sine theta by r square. So dV equals to constant into this, and here the value of constant is mu naught by 4 pi. And where mu naught is absolute permeability in free space. And its value is 4 pi into 10 to the power minus 7. Tesla meter per ampere. And when we put the value of mu naught in this expression, mu naught by 4 pi, we get this as 10 to the power minus 7. 10 to the power minus 7 Tesla meter per ampere. Tesla is SI unit of magnetic field, strength of magnetic field. So this is the basic formula of magnetic effect of current. dV equals to K I dl sin theta by r square, where K equals to mu naught by 4 pi, and mu naught by 4 pi is equal to 10 to the power minus 7 Tesla meter per ampere.